All right. So I want to go through this paper a little bit. And specifically today, I just want to talk through Steins' method applied to diffusion equations. Um, because I think I want to understand this a little bit more deeply, and so I'm going to post a little bit of this up to YouTube channel just so I can keep track of these things and make sure that I'm, you know, explaining this the best I can. Um, so, what's the broad idea? So, first of all, I should introduce what Stein's method is. So, back in around the 1970s, Charles Stein proposed a new technique for measuring the distance between probability distributions. So, what you can see is that we want to measure the distance according to some integral probability metric. So some common cases are um, total variation metric, Wasserstein distance, all this sort of stuff. And we want to understand this, be able to tell the difference between these two. Specifically, based on the central limit theorem, you would kind of expect that if we assume that something is sort of far enough away from being sort of deeply correlated, we should expect that eventually it tends towards something like a normal distribution. And, in the case, in sort of the classical statistical case, where you assume that things are independent, everything's fine, right? There's no problem. And there's lots of really good techniques to get very strong quantitative central limit theorems, but it's actually a lot more difficult once you start getting dependence. It's obvious that, a sufficient amount of dependence will eventually kill the theorem, right? If I just take the same variable over and over and over and over and over and over and over again. It's certainly not the case that 1 over the square root of n times that is going to go to 0 or going to go to anything, right? Eventually it's going to grow like a square root of n and just go off to infinity. So we need some form of decoherence, but it's not entirely clear what are the quantitative requirements there. And so the trick is that we introduce this so-called Steins operator, which acts on a separate class of functions, okay? And we know that we can, for every g in the original class of functions that we want to test against, we can solve this equation. And the only other thing we need to know is that in the original, in the target distribution that we're trying to check, we need to know that the averaged value of a applied to any of our functions is 0. Okay, and so what this allows us to do is ask, okay, going from the difference between an arbitrary function applied to our distribution and the known distribution with that same function, basically just comes down to estimating the supremum over this new test class of whatever our distribution is applied to the diffusion, or applied to the Stein operator. Okay, and so that's sort of the goal of this whole thing, is to figure out, well, what are the conditions that are required in order for that to happen. And so typically we can use like Taylor's, coupling methods, Maevian calculus. Taylor expansion and Maevian calculus really are sort of, in some sense, doing the same thing. Coupling methods are a little bit different. They're a little bit more close to the thing we're going to talk about today. But broadly, you can do the same deal. Okay. Now, the goal is that this was about how do you do Stein's method for univariate situations, or even multivariate, but the point is that you have a single law at a single time. But very often, we're interested in the time evolution of some process, at which point it often makes more sense to think about the law on path space itself. So instead of describing the law at any given point in time, we describe the law over all possible trajectories. This is sort of very natural from like an SDE point of view. or anything like that, stochastic differential equation. Which I think, by the way, I'm going to start a little series on Oxendale, just because I think, A, I should get better at that, and B, Oxendale is a fantastic book. No, sorry, Le Gall. Oxendale is also a fantastic book, but I think I'm going to do Le Gall. I think I like Le Gall a little bit more. Anyways, that's besides the point. So the broad idea is that we want to be able to do this idea, and this was pioneered by Barbour in the 1990s. So how do you extend Steins' method to laws on path space? That's what we're going to talk about today. And then what does that imply for the various things? So this paper is obviously about a large fraction of things, but I want to talk about specifically the portion up to explaining where Barbour's method comes in. So I'm going to be jumping around and doing my own little notes here and there to make sense of this. So, but I want to make sure that I explain this well, so if I don't, let me know. So we're going to start with the space of all Cadillac functions. So what does Cadillac mean? It comes from the French. It means continuer à droite, limiter à gauche. So that means continuous from the right and limits from the left. So a classic example of like what is a Cadillac function is a step function that looks like this. So sorry, this is not that. Something like that. I can't get that to look pretty for some reason. I think because it's, yeah, okay, I thought it was all the same thing. So this is a classic example of what does a Cadillac look like. And the reason they look like this is, if you think about the time evolution of information, right, it's totally possible to be surprised at a given point in time. So we don't necessarily expect the processes that we observe to be continuous from the left, but certainly they should be continuous from the right? If I gradually restrict information, you should not be suddenly surprised by the value along a path. So this is sort of the natural path space when we're dealing with Ito processes, and in general, when we're dealing with processes that are sort of based on information that's gradually increasing over time. And we're going to equip this with the soup norm, so, standard thing for continuous functions. I mean, these aren't continuous, but you understand. So given a function, we mean the kth Fréchet derivative. So first of all, what is a Fréchet derivative? So just to explain that really quickly. So in general, if I have a function, which is from a vector space into another vector space, what I can ask the question is, well, what happens when I do f minus v plus h minus f of v? So in the usual way that this works, right, we would expect that if whatever I mean by differentiable, if I sort of took the derivative of this tending to zero, I would kind of expect there to be like some law. And so in general, what Fréchet derivative means is that there exists an A, okay, and this is a linear operator, just like the derivative is a linear operator. Notice I'm not saying it's linear in its argument, I'm saying it itself is a linear operator. And this is in the linear operators from V to W, okay, such that f of V plus H minus f of V minus A of VH. Okay, and we're going to take the norm of this in the new space, because notice that this is all in the new space, divided by H in the old space, and I take the limit as h tends to 0, okay, this should be equal to 0. Okay. The other way to say this, if you're used to CS notation or Landau notation, is to say that f of v plus h minus f of v minus a of vh is little o of h. Okay, so this is sort of the natural notion of what it means to be differentiable in a Banach space. There's sort of a related notion known as Gateau differentiability, which is really the difference between being differentiable and having all of your partial derivatives. So we can talk about, where does that distinction come from, but hopefully you've seen something like that distinction in Calc 3 or something. Okay, and then of course the kth Fauché derivative is just built up iteratively by doing the same thing sort of over and over and over and over and over and over and over again. Okay. Great. So that's what the Fauché derivative is. And this is the norm that we're going to attach to that Fauché derivative, sort of the natural thing you would expect from a multilinear form. Okay, so we're going to start with the Banach space of all continuous functions for which this norm is finite. We're going to get some intuition as to why this is the space later. But broadly, you can just think about this as like a certain weighting of the space. So we want to be able to consider not just functions where they're bounded, but that they have some sort of quantitative dependence on W. They don't grow too fast. But really, fundamentally, what we're actually going to be interested in is these sets of functions. So you can think about this as like an extension of C to Lipschitz. So we want that the second derivative of our function with respect to the underlying variable behaves like a Lipschitz function. And that's pretty much it. Okay, so that's the broad idea. Yeah, okay. And then the claim is that actually if you have this and you have this, in fact you have this. And really what I want to sort of point out when I'm doing this is the fact that really this is the foundational object. And this gives you this, and in fact this. So you may have noticed that this says that this subset, this is a subset of this. And so let's take a moment and actually prove that. Okay, so we're going to start with these functions. So claim if the supremum over W and H not equal to 0 of f of W double prime plus H minus f double prime of W divided by the norm H is less than infinity, then the supremum over W of, I'm sorry, these should be G's. And G of W over 1 plus W cubed is less than infinity. So if I just tell you that this is C2 Lipschitz, I think that you would believe that this is probably the case, but let's prove it explicitly. So the goal is going to be to get some understanding of this. So we know then that G of W plus H minus G double prime of W is less than or equal to some thing times the norm of H, right? Obviously. And so in particular, g double prime of w minus g double prime of 0 is less than or equal to kg norm of w. And so g double prime of w is less than or equal to g double prime of w minus g of 0 double prime plus g double prime of 0, which is less than or equal to kg w plus kg tilde of w, I'm sorry, of just kg tilde, because this is just some number, right? I mean, for every g, this is just some number. So because we know that it's a second Fauché differentiable, so the Fauché derivative exists, in particular it exists at 0 and it has some norm, right? So this is less than or equal to kg of 1 plus w. By the way, I'm going to let the derivative change, or the constant change from line to line. If you want, you can go through and get all these things with very nice constants all the way through, but I'm not going to worry about it. Okay, so this is the first statement that I want to make. And so actually what you might notice here is that this says that g double prime of w over 1 plus w, that this is actually finite. And so actually, we've already shown that I believe this is a typo. I'm pretty sure this right here is a typo. I'm pretty certain that's a typo. I have to think about that for a little bit more, but anyways, I'll come back to that. Okay, so that's that first term. The second term, and by the way, we won't need that, right? What matters actually is that this is less than that. So. Okay, so second term that we want to bound is g prime of w. And so I'm actually going to do this in a slightly more roundabout way, just because I want to be super careful and safe and, you know, all this good stuff. So I'm actually going to fix an h, and I want to bound the size of this thing. And in fact, because this is mapping into the real line, this is in fact a linear functional. Okay, so what are we going to do? Well, we're going to do basically the same trick. So we're going to say this is g prime of w h minus g prime of 0 h plus g prime of 0 h. Okay, and this is clearly less than or equal to, I'm going to make this big here, so 0 to 1, g prime of tw, like this, and then h w dt plus some constant times the norm of h. Okay. And so this is clearly less than or equal to the supremum over t in 0, 1 of norm of gt, g double prime of tw, times h, norm of h, norm of w. And of course plus k, g, h. Okay, well, we know what this can be bounded by because we've already seen this before, right? So we already know how to bound that. So this should be less than or equal to, I'm going to pull out the H. So this is going to be kg, magnitude of W, times 1 plus the magnitude of W, plus kg tilde. Okay. Now, this has a term of W in it and another W in it. And so actually you can bound this whole thing by another constant, whatever it is, times 1 plus W squared. Okay? And this holds for every H. So in particular, G prime of WH over the magnitude of H is less than or equal to kg of 1 plus W squared. And then we take the supremum over H to obtain that G prime of W is less than or equal to kg 1 plus W squared. And of course, that's exactly what this is. Okay. And now you can probably see the pattern as to how we get this in the final analysis, but let's just do it. So G of W is less than or equal to G of W minus G of 0 plus G of 0. This is equal to the integral 0 to 1 G of TW minus G prime of TW W dt plus G of 0, which is less than or equal to the supremum over T in 0, 1 G prime of T W times W plus kg, which is less than or equal to the supremum over T in 0, 1 of 1 plus TW squared times magnitude of W plus kg, and I hope it's pretty easy to believe at this point that this is less than or equal to 1 plus W cubed. Okay. So that's the proof that this Lipschitz-looking condition, this thing, is actually sufficient to tell you that you're in this one, and we can construct an explicit norm out of that. Okay. So, once again, be super clear. This is a larger space than this, okay? But this is going to be the core space that we're concerned about. Okay. And really, we're going to be concerned about some functions that have some extra properties. This is going to be the big one for us, which, I'm trying to give a good interpretation to, but it's something like, being in the space that you generate a controlled rough path. I'm not quite there in terms of, is that exactly what this means? But it's something like that. It's something like, at any given point, if I sort of evolve according to my system and take the expected value of the difference, then I'm getting something like a controlled rough path. But anyways, that's besides the point. So that's all of that. And now I want to walk through, I'm going to skip a lot of the paper because, these are all great points that I want to get to eventually, but right now I just want to focus on the portions of the theorem that I want to show. So now that we've proven these conditions all follow, we haven't proven this one yet. This one is effectively just Taylor's theorem. So we know from Taylor's theorem that g of w plus h minus g of w minus g prime of w h is equal to 1/2 g double prime of some number times h2. So this is h in both portions of this bilinear form, where this is between w and w plus h, so it's w plus th for some t. In fact, let me give it that explicit form. This is w plus th, and then h2. And so now what we can do is we can say, well, okay, so g of w plus h minus g of w minus g prime of w h minus 1/2 g w prime of w h of 2 is equal to 1/2 g double prime of w plus th minus g double prime of w, okay? And then both of these are applied to h2, and now you can kind of see what happens, right? So if we take the absolute value, we can bound this by the norm of this, and then that's where the Lipschitz-like condition comes in. Okay, so we're able to obtain this, and so now what we want to do is we want to derive a Stein equation for this approximation by using a generator of a Markov process. So we're going to generate a Markov process such that the stationary distribution is exactly the distribution we want it to land at. Okay, so here's how we're going to do that. So I'm going to create a collection of random variables. They're going to be an IID collection of Ornstein-Uhlenbach processes with a stationary law n01. And importantly, x is going to start off as n01. So one of the cool things about the Ornstein-Uhlenbach process is the fact that because this is its stationary distribution, if you start in that, it's obviously going to stay there forever. It doesn't mean that there's no sort of internal correlations between time steps, of course, but at any given point in time, this is always an n01 random variable. And so now we're going to use the Schauder function construction of Brownian motion. So if you're familiar with the Karnin-Love expansion, this is the same thing. So the idea is that any of these Markov processes, we can expand their laws on path space, assuming they're Gaussian processes, as a sequence of sort of eigenprocesses, for lack of a better term, times sort of independent n01 random variables. Okay? And the construction of those is fundamentally related to the well, I'm not going to have time to get into that, I guess, but just sort of the abstract Wiener calculus. Okay, so just, you know, I hate saying this, but if you can, you know, take it from me that this is a genuine expansion of Brownian motion, is to say that for every given time, you just take a bunch of n01 random variables and you multiply them by these specific Schauder functions, which you can kind of see as being integrals of these Haar functions. And so in some sense, you can actually think about this as a multi-scale expansion for Brownian motion. Then this is going to work. Okay. And so the function from t to u is almost surely continuous. The way to think about that is that all of the path laws themselves are continuous, and of course the functions themselves are continuous. So sort of in a weak argument sense, the point is to say that these things are going to be almost surely continuous across the board. You have to be careful about that, of course, but it's not as bad as it may seem. So the following two equations correspond to equation this. So the point now is that now that we have found some representation of what our process looks like, we're going to define this as a new process on path space, right? Which is sort of generated by each of these components underlying it, and now we're going to simply check what the distribution is going to be like. And so the key point is that we are going to have this infinitesimal generation of the process acting on any f, and we're going to show it's actually related to two different things. One is a first derivative applied to w, okay? And then the other is the expectation of the second derivative with the 2-point process. So what this means here is that, we already seen this before, but the point is that this is the random process where for each evolution, we're going to sort of fully track out all of their sort of pair correlations and use that within this. Okay, and because that we have this nice little representation, it's actually clear that when you take the expectation, due to bilinearity, the only thing that survives is, of course, the terms that where k agrees, and those are those terms. Okay, so this gives, we want to give a proof that this is the actual form. So what we're going to do is that we're going to actually figure out what is the semigroup acting on F and see how it goes. So in order to understand the semigroup acting on F, all we got to do is push forward this W by the semigroup, and then by a certain amount of time U, and then we're going to figure out the expected value here. So this is going to be the expectation under F of W applied to E to the minus U. So this is whatever the path started as. We're going to sort of let it decay down, and then we're going to add in a new Brownian motion that's totally independent of what we have so far, on top of it with this scaling factor sigma of U. So sigma of U here is just the square root of 1 minus e to the negative 2u. You can think about it as sort of just a scaling factor to make sure that as this term is decaying, we're sort of maintaining the rest of it. Okay, and based on that same thing, you can kind of tell that this is probably going to be true, where if I evolve this according to a certain amount of time, and then I downweight the previous amount by e to the negative nu, or the time difference, well, this is going to kill off sort of the deterministic part, and of the part that's going to be remaining, there really only should be this sigma of u z term. Okay? Which is, in this case, just going to be the sigma of the difference. So now we want to break this up into some terms that are easier to understand from a U perspective. And really, we don't care about anything above first order, because what we're going to do later on is that what we really want to do is take U down to infinity, and so anything that's order U squared or U cubed or whatever is irrelevant to us. The real hard thing at the moment is that this isn't related to any sort of process that we can understand, but we're going to see how we can get around that. So this line, if you're reading this paper for the first time, I think looks very strange, because it's not really clear what you're doing. But the point is that we want to understand this object right here, right? Because we claim that this thing goes down to 0 in order for this thing to truly be the Frechet derivative. This is sort of how it has to go. Or not the Frechet derivative, it's really just the derivative. So this is what we want to understand. And we want to break it up in terms of these quantities. And how are we going to do that? Well, we're going to have these things replaced with these things. And so I'm going to walk you through some of those. A lot of them are not so bad. So, I mean, this one's really easy. So this one, all you have here is 1 minus e to the negative u. The idea is that we can prove that this is the same as u plus o of u squared. Again, that's actually not that hard to show. In particular, we know that 1 minus e to the negative u is equal to u is equal to 1 minus 1 minus u plus u squared over 2 minus u cubed over 6 plus so on and so forth. And so the key point is that if I move this over, right, then I get that 1 minus e to the negative u is equal to u plus some terms that are at least order u squared. Making that a little bit more formal is a little bit more work, but it's not that big of a deal. So what we can do is we can take this u right here and just replace it by a 1 minus e to the negative u term. That'll pick us up a u times f prime of w term, but that's actually okay because we already have a bound on f prime of w, so we know that f prime of w is in M, because that's what we're trying to define this on. And so actually we can just bound that term explicitly by this first term. Okay, so we know that we've made some mistake by exchanging that u for this 1 minus e to the negative u, but that's okay because, we know that f prime of w is just going to give you some term that looks like this. Sorry, no, I think it's this term. I think that one corresponds to this term. Yeah, I think so. Same thing goes for this one. So sigma squared of u is 1 minus e to the negative 2u, which is, of course, just 2u plus o of u squared. And then this is acting on z2. Okay, so that's okay, right? It's not that big of a deal. So this is effectively the same as this term. It's just now that we have that, we just have to take a bound on this. And then that's going to give us a term that looks like this. Okay. All right. Great. And then we just need to take a term that looks like this and get its bound. But this is super easy because this thing is, again, roughly u plus higher order. And so when we square it, it's u squared plus higher order terms. So from the perspective of u, this term is irrelevant. And it's just going to pop us up another factor that looks like this. And so these are all controllable terms. We have them all. They're fine. All that good stuff. So that's that, I believe. Okay. And so this may seem silly at the moment. It's clear, okay, we were able to exchange it by some other terms, and that's fine, and not a problem. But what does this mean, right? Like, this is just some sort of gobbledygook. It's not really clear what is happening to any of this, other than that, you've changed some variables. But now we can go back to this original representation, right? So we know Brownian motion is distributed like this z of t, which is just any 0, 1 random variable applied to sk of t. And we know, therefore, that because it's mean 0, right, for f prime of w, we're going to get a 0 variation. You really can just imagine that by each of these SKs. Acting on each of them, they're bounded linear functionals. And so, you just need to make the limit that they exist, and that involves, some basic actions. So same thing happens for the anytime you only have it show up once, right? The only things we really care about from the mean perspective are when the same thing shows up twice. And then we just want to use the inequality that 1 minus e to the negative u is less than or equal to u for u greater than 0, which is kind of obvious. So we know that this is a term that is going to grow like this, and then, sorry, I didn't get that perfectly lined up. Let me delete this and try again. versus this negative x term. And there's lots of ways to actually prove that it's always better, but I'm not going to do that. It's a basic, calculus lesson. It's clear that they're equal initially. I guess I am going to prove it. E to negative u. So this is the derivative of the right-hand side. Derivative of right-hand side. And derivative of left-hand side is 1. And so it's obvious that the two functions are equal at 0, but then the derivative on the right-hand side is always less than the derivative on the left-hand side for every value. And so therefore, they're always going to be less than each other. Okay, great. All right, and now so we just want to bound this R now that we've gotten into this strange form. But what's nice about the form that we got it into is if you look at it, this, let's see if I can find it in the original. So we're allowed to add back in an arbitrary copy of Brownian motion because of course it's mean 0, so it doesn't matter. And we can do the same thing here. And we're just going to add 1 for each. So notice that we have each of the individual terms here. There's nothing stopping us from adding in the terms together. And yeah, so that's what's going to get us to this. And now what we notice is, well, this is just another copy of the Ornstein-Uhlenbach process, right? So all we have to do is then take out this f and say, well, this thing is certainly bounded by some constant times this norm of whatever this silly thing is to the cubic power. Well, let's see if I have a good explanation as to why this is true. So the reason why that's true, right, is because of this. Right, so we proved this earlier, which is that just based on this Lipschitz-like condition, we know that we're going to have this sort of generalized thing. And this is exactly the Ornstein-Uhlenbach process plugged in, right, into U, into W. This is, of course, the original. This is the derivative applied to that. So this is effectively our h, and then this is our h squared. So we get that this is the h cubed, and then we can pull out the f out of the expectation, keep this in there. And so now all we need to do is get some bounds on this. So the point is now we're going to be able to use this term. So the idea is going to be that we break this up into, let's see if I can think of the correct way to frame this. So, well, the first thing to say is 1 minus e to the negative 2u is, of course, less than or equal to 2u based on that. And so sigma of u, which is just the square root of this, is, of course, less than 2u. The question now becomes, where do the cross terms go here? Oh, yeah, sorry, yes, of course, obviously. So this is sigma of uz minus w1 minus e to the negative u infinity cube. And so this is equal to, or less than or equal to, sigma of u times the infinity norm of z, which is, again, z is just a random variable described at some time. Right, because again, z is just some random variable plus u, and w is going to be the infinity norm. And we're going to cube it. Okay, and then of course this is less than or equal to, again, these are positive numbers. They were in a cube, so if I raise their coefficients, obviously I raise the whole thing. So this is going to be 2u norm of z plus u norm of w infinity. Break that up and cube it. And so now, all I need to be able to do is take this expectation and obtain this, okay? And so fundamentally, what this relies on is just determining some moments of expectation of z squared, expectation of z cubed, and expectation of the absolute value of z. And so these are just some moments of a Gaussian random variable, and obviously they're finite. So the leading term, of course, is going to be w cubed, and the lesser term is going to be 1. And so now we just need to know the leading term here in terms of u. So this is kind of where the key is that we need to make sure that this thing is less than 2. That's really or sorry, no, it needs to be greater than 1. Sorry, that's the main thing, is that this term right here has to be this term right here needs to be greater than u to the 1, because we're going to divide it out by u, and we want this to go down to 0, right? Okay. And so what we need to look at here is, like, what is the lowest order term that's multiplying by z, okay? And so in this case, that's going to be this square root of u. In reality, right, we could have really done this whole thing by really just stating that the square root of 1 minus e to the negative 2u divided by u, the limit as u goes down to 0 of this is 0. But, you have to be a little bit careful. But fundamentally, that's sort of the main thing that matters. Okay, so based on that, we're able to now, we've done all this, right? The whole point of this was to get this weird looking expression to look like this, and then we can just use some properties of Brownian motion, or really properties of the normal random variable to obtain what that should be. And so the important thing here really is the sigma, right? That's the main thing that really determines. And the Markov property allows us to make some nice assumptions here. I'm saying all these because at some point I want to extend this method in various directions, and so I want to understand kind of where are the limitations. Anyways, so all of that is to say that on this process, we've been able to define this limit explicitly as this decreasing space of this thing. So on the closure of this space, we've actually shown that this is a strongly continuous operator in the sense that this is a closed linear subspace that has a generator defined everywhere. And so what we would want to do is be able to extend this to the whole space. Now, this is just for M. And so if we want to extend this to M prime, right, which was this weaker space, this has this condition, which is, again, I want to interpret this as something like the ability to say that like f of the process is still a controlled rough path of the original process, or really of Brownian motion. But I have to sort of prove that that's actually what this is. And we just want to show that in this case, we get the same sort of general thing, except for JT instead of for Z. And because we went over it a little too fast, let's go back and talk about what JT is. So JT is just the step function, okay? So it's really just the step function. And so this is really going to stand in for the these Haar functions. Okay? So instead of doing these Haar functions, we're going to do these GT. Okay. And so that's exactly what gets us to here. And the proof here is actually relatively straightforward. So the thought is that we basically say that instead of defining this equal, we just need to show that this is equal to this for these types of functions. So remember that these aren't in M anymore, they're in this M prime. So it's not actually clear that this exists. But the way we're going to do it is basically a discretization. So we're just going to look at it a sequence of points. And each of them has the same distribution as Zn. And now we're going to do the same trick of we're going to add and subtract by nice things that are mean 0. Until now, we're able to break this up into a term which is independent of the expectation, but only involves f, and then one term which is z minus gn, and another term which is really just z. So that gives us that. And then by Cauchy-Schwarz, we're able to bound this. Notice that this involves the expectation of the supremum over the thing of zt squared. This is one of the reasons why I want to do a thing on Legall, because I want to be able to show you that that's true. But for now, just take for a grain of salt that is just some constant. That we're just going to be able to say that the expectation, the supremum of t in 0, 1 of z of t squared is some constant. Okay, it's not obvious at all that that's true, because you're dealing with sort of an arbitrarily large path space, and so it's really not clear that this is going to be true in general, but it is true. So I'm gonna have to show you that by showing you Legall. Okay, and so now we end up with this. So we have the supremum of t in 0, 1 of the difference between zt and sort of its nearest neighbor from a squaring perspective. And we're able to represent this as log of n over n, which is related to the law of the iterated logarithm. And so, of course, as n goes to 0, we're getting something like log of n. Sorry, as n goes to infinity, we're getting something like log of n over n to the 1/2, and so that's going to decay down towards 0. Okay, and so that allows us to transfer from this to this to this, and then of course we know that this is equal to this by the definition of n prime. Okay, and so now we want to show some existence and properties. So I want to, again, bring up this point because this was a mistake in Barbour's original paper, but, the paper's great. I'm not, criticizing, I'm just saying this was a mistake. So this semigroup is actually not strongly continuous on the original space that we're interested in. It's only sort of strongly continuous on a closure of the space that of M. But we are able to get that if you do something like the resolvent, then and you sort of send it down to 0, then as long as you mean 0, then this whole thing will go through. Okay. and you just need to, I'll do this, I think, another day, because it's already going along quite long. But yeah, so this is an additional one that allows you to just take it explicitly, and you can figure out what is the derivative explicitly, and it turns out to just kind of be what you would expect it to be. So this is something like a resolvent trick. All right. And now we can extend this from M0. This is sort of an extension of our result from 34, but just to follow it through so that we know that this kind of all goes through, and everything works out. So I'm not going to be too interested in that at the moment. And so the point is, suppose that G is in M0, so it's in this space that has this C2 Lipsch condition, and then also has this condition, which is something like a controlled rough path condition. Then you, of course, have that if you subtract off its mean, then its mean 0, obviously. And it's still in M0, so the constant doesn't change anything. And so by this previous result, we can find for any d-valued random variable x, we know that there is f in M prime such that it's equal to this h, 5h, which is, of course, again, constructed via this resolvent-like construction. And so we're able to say that the expectation of mu of gx minus the expectation of g of z is equal to, the expectation with respect to the law of x of negative f of x plus the integral of f of x gt. And right, so again, up until this point, we have used nothing about x. That's a key point. We've really used nothing about x. We've only used properties about the limiting distribution that we care about. We don't really use anything about x, which is part of the point. Okay, anyways, sorry, this is getting a little long. I hope this is like an okay explanation. I'm probably just going to throw it up there just, again, to get over the anxiety. But my hope is that I'm going to continue explaining these things more and more, both to help me and maybe hopefully to help people out there. Eventually, I will sort of talk through this entire paper. It's a really good paper. I highly recommend reading it. This is a set of authors that are working a lot on applying Steins' method to dynamical systems. And so I'm interested in their work, and I'm going to be following it closely. Okay, great. Well, thank you so much for listening, and I will be back on.